Thanks again. Thank you very much to the organizers for giving me the chance to present this work. And I'm going to address a general question. If you have two particles in an interacting many-body system that are scattering off each other, wouldn't it be nice to know how strongly they scatter and know that as a function of both the incident energies of the two particles and the energy transfer? And you would like to know that at arbitrary temperatures and without having to make uncontrolled approximations like mean field, etc. So that's generally the question of how to compute a two-particle vertex for a many-body system. And in the context of quantum impurity models, which is something that I've been working on for a long time, it's been a dream of mine for at least 10 years to be able to compute something like this. And I'm very happy to be able to tell you today we managed to achieve that together with Fabian Kugler, who was a PhD student and then a postdoc in my group at the time. He's here. He will give the talk after me. And Seung-Sub Lee, who was a postdoc in my group and now is professor at Seoul National University. It was quite a challenging project, and it took two really dedicated and gifted coworkers to get it to work. But we managed to pull it off, and the work was published in two back-to-back PRX papers beginning of last year. And the method is NRG, Numerical Renormalization group. It allows you to zoom in to arbitrarily small temperatures and frequencies in a very controlled way. And we were able to use that method to compute for quantum impurity models 4-point functions in both Matsubara formalism and the Keldysh formalism as a function of 3 frequency arguments. I think it's something very useful, and I hope I can explain to you how we did that. So my goal in this talk is to give you some glimpse of how NRG works and how we got this calculation going. And so at least a substantial part of my talk is going to be methodological. And I will start by explaining NRG methodology for 2-point function, that is review of standard methods for at least more than 25 years, but with improvements that came over the years. And then to advertise how well, or with the power of NRG, I decided to bring 2 applications that we have been pursuing in my group. One on Hund metals, involving a combination of orbital and spin screening. And the other one on Heavy-fermion systems. That's basically a brief advertisement for a poster that will be out on display this afternoon. And then towards the end, I will go forward and explain how one generalizes this methodology to 3-point and 4-point functions. And I will not dwell very much on results because Fabian will be giving the talk right after me, and he will discuss the results in great detail. So thanks to the organizers for giving us this double header chance to present our care. And then I end up with conclusions. All right, so my goal really, some of my slides will be technical. So maybe in contrast to this morning's talk, this is really focused on methodology. I want to give you some glimpse how this method works. I assume not everybody in the audience knows about the intricacies. And the basic idea of energy is actually not that difficult to understand, and I'm trying to get this across today. So the setting is that you have a quantum impurity model, meaning you have a localized quantum degree of freedom, a spin or a localized d orbital in a metal coupled to a bath of excitations that are non-interacting. This is also the setting that you encounter in dynamical mean field theory. We have to solve an impurity model self-consistently. And you want to do that in a way that resolves low energy degrees of freedom very accurately. And the way how to do that was figured out by Ken Wilson in 1975 as part of his Nobel Prize winning work on the renormalization group approach. And in order to resolve low energies, what was that? His idea was, let's discretize the conduction band in a logarithmic fashion so that you can get high resolution, many discrete intervals at low energies. There's typically a parameter lambda that is bigger than one that governs this logarithmic grid spacing. And then you can map this system to a quantum chain model where the impurity degree of freedom sits at one side and the bath degrees of freedom are arranged, linear combination of these along a chain, just a tight binding non-interacting chain, which has a particular feature that the hopping matrix element along this chain decay exponentially as you go the chain. This energy scale separation is directly inherited from this logarithmic discretization and was one of Wilson's key original ideas. And then you say, all right, since the coupling along the chain decreases exponentially, it makes sense to diagonalize this chain one side at a time. So you take a short chain, let's say 3 or 4 sides, diagonalize it exactly on the computer, and you get a discrete set of states. And then you know that if you're going to add more and more sides, your Hilbert space will become bigger and bigger, and you'll have to make some truncation at some point. So Wilson says, let's split the spectrum into a set of kept states and a set of discarded states. And then you add another side, and you only keep track of, you only use the kept states together with a new site to compute a more finely resolved spectrum. So you resolve the low energy part of the spectrum better, the high energy part you don't keep track of. In that sense, you discard it. And then you add another site, you resolve the, you first discard again the high energy parts of this shell, and so on and so forth. You add more sites, and in this way you resolve the low energy part of the spectrum more and more finely. If you keep doing this for a long chain, then you can actually follow the renormalization group flow as you lower the characteristic energy scale of your system, which is governed by the chain length. And if you plot these lowest line excitations in a manner rescaled by this characteristic energy splitting, you find crossover between fixed points where the rescaled eigenenergies are independent of energy scale for a while, then they cross over and then they reach another fixed point. This is a crossover for the single channel Kondo model between a regime where at high energies you have a free spin, so-called local moment regime, and then low energies you get a Fermi-liquid regime where your local spin is screened. So this physics, of course, is well known since the 1970s, but Wilson was able to characterize it very explicitly. And these types of diagrams are very useful also if you study more complicated models to figure out what the various fixed point regimes are. And then if you do a fancy implementation, you can keep track of quantum numbers and use treat models with high symmetries, etc. All right, now that in itself is very useful, and Wilson got a lot of interesting results out of that in his original publications. But then people also wanted to compute spectral functions. That started in the late 1990s. And for that, if you want to do that with spectral representations, you need a complete set of basis states. And I just told you one throws away some basis states. So let me describe how you can construct a complete basis in this setting. So let's go through the same scheme again. We diagonalize our short chain, introduce kept, but before we start throwing away sites, we realize the short chain has an environment of the rest of the chain that you've not treated yet. And so instead of ignoring that environment, you say, let's just embellish this short chain with the environmental states, and in that sense generate a set of discarded and excited and kept states together with the environmental states. And now you make the chain longer, add another site, refine the kept sector again, and again add the environmental states to these new states, and keep going. And now if you look at what you get in the end, if you gather all these so-called discarded states, which also know about the environment, you actually generate a complete many-body basis for your entire system. You're not throwing away information. And one can formalize that by saying you introduce a projector onto the end shell involving either kept or discarded states. And if you sum up all these projectors, you actually resolve the identity on the full chain. And that you can use to compute dynamical correlation functions. If you have a complete basis, Lehmann representation, or things like that work. This was figured out. So this idea is due to Fritjof Anders and Avi Schiller. I like to call this Anders-Schiller basis. And what's nice about this basis, it's built from approximate eigenstates of the chain, right? So the early states you refine, you refine the energy coarsely, and for the later states along the chain, you have a more fine resolution, the smaller degeneracy, but you keep keeping track of all the states. All right, so with that one can compute spectral functions. Let me review how it's done for two-point correlation functions. So let G be a two-point function. I'm going to, for example, for argument's sake, just consider the zero frequency formalism. One can do it in Matsubara or Keldysh formalism also. Then you can write this in the following form: a product of two operators times a theta function, taking care of the time ordering, and then summing over both permutations of these two times and a sign factor. And if you then Fourier transform this and use convolution theorem, you get a natural factorization into a convolution kernel, which is just one of frequency denominator. And then this, what we call partial spectral function, which is just built from matrix elements of the operators and delta functions, which pick out those energy differences in these transitions that come with a specified frequency. Right, so these are the objects that you need to compute numerically. My notation here is E sub I is an eigenenergy, exact eigenenergy. Now this is a general formula. These are the matrix elements. And if you're able to compute these objects, you can compute spectral functions and correlation functions. All right, and you, as I said, you can use any method that can get you these eigenstates. If it's a short system or small system, you can use exact organization, but we will use NRG to compute them. All right, and now the question is, so how do we compute these matrix elements? Now first, minor side point, we get matrix elements decorated with energy conserving delta functions. So you can define matrix elements that depend on energy, meaning you separate the set of all matrix elements into ones with specified average energies. Okay, we call this slicing. This is just a technical remark. And then in that sense, you can write this expression as a trace of density matrix times first operator sliced at a given energy times the second one. And now let's think how this information is gathered in the numerical renormalization group. We can refine these operators shell by shell. You have to compute matrix elements. So if you take an early shell, you get a coarse-grained view of this operator where you have matrix elements only at high energy differences. And then if you split this into kept and discarded state, it also splits this matrix into block diagonal into blocks. And they are labeled by discarded, discarded, or discarded kept, etc. And then at the next iteration, where you just refine the kept sector, you refine this lower block here. You refine that more and more, and then you can keep going. And as you make your chain longer, you refine the lower energy matrix elements with small energy differences. Refine them very well. And this way you can represent an operator as a combination of contributions from all shells in a more and more fine manner, and you can really zoom into low energies. And this you can then put together and get an expression of this type. You know all these energies explicitly. All right, so that's in a nutshell how standard NRG works for correlation functions, two-point correlation functions. And so let me now show you some two applications. I don't want to go into too much detail, but just to give you a flavor of what one can do. So my first application is from the field of Hund's metals. Those are wideband materials with several different bands, where there's an interplay between Coulomb interaction and Hund's coupling. And in a collaboration initiated by Guy Kotler, over the years, my group has written quite a number of papers, all the people involved. And I don't want to put on all of them, but just give you two 2 or 3 highlights of that. So the way we treated Hund's metals was from a toy model perspective. We wanted to understand this interplay between Coulomb interaction and Hund's coupling in the simplest non-trivial setting. And so we studied a model which had been proposed previously by others. It's a 3-band model where you have you can put up to 3, well, you have three orbital levels. And we studied at a filling of 2, so that there's, in the presence of Hund's coupling, there's a total spin of 1 there, and it's an orbital triplet because this hole can sit in any of 3 positions. And so the impurity now has spin and orbital degrees of freedom. And we, the model, as we set it up, has high symmetry, so we could use methodology developed by Andreas Weichselbaum for tracking symmetries. And then we use DMFT on a beta lattice, and then it gets mapped to self-consistent Anderson-Hund model, which we treated by NRG. And that allowed us to pinpoint some issues that were, at the time, 2015, not fully understood. So what I show here is the spin and orbital susceptibilities as a function of frequency at 0 temperature. And what one, in this representation, if you have a peak in this imaginary part of the spin susceptibility, that means the relevant degree of freedom gets screened. So here we have orbital screening in the red curve, and then spin screening in the blue curve, and they occur at somewhat different energy scales. And this is an indication of what we call spin orbital separation. As you lower energies, and the energy at which you probe the system, first the orbital, this should be orbital triplet, sorry. The spin 1 orbital triplet gets screened into an orbital singlet, and then the spin 1 turns into spin 3F because 1 electron from the bath gets bound to the local spin. And then in the second step, the spin gets screened. And the interesting point is that there's an energy range between these characteristic temperatures, orbital and condor temperature, in which you have slowly fluctuating spin degrees of freedom, or the orbitals already screened. And that gives rise to, for example, the local spectral function, a sort of a sharp peak structure on the spin width of the spin condor temperature with another shoulder. And in this intermediate regime, yeah, one gets, as I said, slow fluctuations of large local moments. This is something that's been called spin freezing in the literature previously. And it gives rise actually to weird behavior, in particular also a non-Fermi-liquid behavior. And so we wanted to understand this in some more detail. Is this intermediate regime governed by some non-Fermi-liquid fixed point? And to analyze this, we decided to do the following. One can, so DMFT maps this 3-band Hubbard model onto an Anderson type impurity model, in which the parameters are sort of given by just by this DMFT mapping. And then you can simplify this by mapping it to a condor type model with a Schrieffer-Wurf transformation. And then you have a spin exchange and orbital exchange and spin orbital term. And the parameters here are also fixed from the starting point. And they're fixed in a way that the spin orbital degree of freedom, the spin orbital window is quite small. But so Gabi had the idea, let's detune the couplings of the condor model by hand. So it's now detuned away from the initial model, but in a way that one can widen this window of spin orbital separation and try to understand better what's going on there. And this curve that these two curves shown here in green and red for the initial parameter regime of the Hund's, of the Hubbard-Hund model looks like this. So it's fairly narrow. But if you then tune this this coupling, this condor coupling all the way to 0, you can open a very broad energy regime. In NRG, you can zoom into over many orders of magnitude and then try to understand that regime from a theoretical perspective. And it turns out you then flow to, you always flow to a Fermi-liquid fixed point at very low energies, but this intermediate regime is pretty large. And one can then, in this intermediate regime, figure out the screening from the spin 1/2 orbital triplet to the full screen system happens through an intermediate regime which we call spin splitting. And in that regime, one can actually, we get very clear, strange power laws in the spin suitabilities, which one can understand using arguments from conformal field theory. And there's actually a non-Fermi-liquid fixed point governing this behavior. So I mean, this is now maybe a little bit academic from the perspective that non-Fermi-liquid fixed point is not reached in the real systems, but the power that we find here actually does match this low shoulder here. So one can argue the system is in a way governed by non-Fermi-liquid behavior. All right, so with this story, I wanted to indicate that you're really able to, with energy, go to very low energy scales if you so care, and if the questions that you want to understand require that. Then, going to the other side, towards a direction of being more realistic, I also want to briefly mention a project which Fabian Kugler did together with Anton George and colleagues at the Plattan Institute, where they studied strontium gluconate, which is a very well-studied material experimentally. And it's known that it has a Fermi-liquid scale, which is fairly low, around 25 Kelvin. And it was not clear a priori why it is so low. And so Antoine suggested to do a DMFT, ab initio, a DFT plus DMFT study, and then use NRG to try to reach very low energies. The bare band structure has some Van Hoff singularities. And if one then does NRG on top of that, one can see how they get shifted, and you can study in detail the behavior at very low energies and get a crossover scale towards a Fermi-liquid behavior, which actually matched pretty nicely with the 25 Kelvin. So again, if you want to know more details, talk to Fabian. He's here. I just wanted to show this briefly to indicate that this methodology is sufficiently well developed now that one can also make contact with material type of questions if that's your interest. All right, and in the last application, I want to say a few words about DMFT plus NRG applied to heavy-fermion system. This is work done by Andreas Gleis, who's here, who has a poster this afternoon. And we studied the periodic Anderson model, which is a model where you have delocalized electrons, a lattice, 3D lattice of delocalized conduction electrons. And on every lattice side, there's also localized F electrons. And Hamiltonian has Kondo interactions. And there are also RKKY interactions that get generated through this periodic Anderson model. And the competition of these two gives rise to this well-known schematic phase diagram. There's a Kondo phase where these conduction electrons screen the local moments. And then there's an RKKY phase where the spin exchange between neighboring spins, local moments dominates. And then there's supposed to be a quantum critical point in between. And this was been studied going back to the late 2000s using Convan-Akala methods as impurity solvers. And they uncovered interesting physics, but they were not able to go very low down to this critical point. And now, as you will see on Andreas's poster, he's able to, well, he worked out this phase diagram in detail. So this is calculated data. And it can go really low to this quantum critical point and study what's going on. And what we find is in this RKKY phase is actually a very narrow band next to the band structure that you get from the hybridization between the conduction band and the localized ones. Bandwidth set by the Fermi-liquid scale, this one, which becomes extremely low as you go to low temperatures. As you go to the critical point. One can compute the Hall coefficient, which shows a step-like crossover if you go across this critical point. And that's actually reminiscent of something that people measure in related materials. So qualitatively that matches. And then Andreas also computed the optical conductivity as a function of frequency and temperature, found some interesting scaling behavior, which actually is qualitatively related to what's found for such materials. So the resistivity here shows bad metal behavior over a large region. In this plot, this is conductivity times temperature. If that is constant, that basically means that you have this linear T resistivity, which he finds in this region down here for temperatures below the, above the Fermi-liquid scale, but below the non-Fermi-liquid scale. And then this frequency scaling here, T over omega scaling, is also found in related experiments. So I hope this little teaser encourages those that are interested in this type of physics to visit that poster. All right, now let's get back to the main topic, 3 and 4 point functions. Okay, having seen what energy can do for 2 point functions, it would be, well, as I mentioned, for a long time I was interested to see whether we can generalize it to 3 and 4 point functions. And the starting point is that one realizes that this formula that I showed you at the beginning for 2 point functions can generalize quite nicely. Fabian will explain this in more detail in his talk. But the basic idea is if you now have a product of L operators, a time order product of that, you can again arrange it as a product of these operators themselves, decorated by a product of theta functions, which induce the proper time ordering, summed over all permutations and corresponding signs. And if you then Fourier transform this, you get the structure that you have a convolution of a convolution kernel and partial spectral function. Convolution kernel is now more complicated, but you can write it down by hand. The partial spectral function now involves a set of L matrix elements over O. If it was a 2 point function, you had two matrix elements, now you have L of them, decorated by energy conserving delta functions. And in Fabian's talk, he will discuss these various convolution kernels briefly. My focus is how to compute these partial spectral functions that have now a more complicated structure. This slide is borrowed from Fabian. He will explain to you that they are that you can apply this for different formalisms, zero frequency or Matsubara or Keldysh. The only thing that changes is the convolution kernel, but the partial spectral function is the same for all of them. So if you can compute that with NRG, we're in business. All right, now as a reminder, the 2 point spectral function that I explained earlier has this structure. So it's a trace of density matrix times one operator matrix elements of that times another one. And I explained to you that one can resolve it to very low energies by just iteratively refining the kept sector of the previous iteration to get this type of structure. Now, for 3 point functions, my pictures will just be for 3 point functions, but the DSM for 4 point functions. What you end up with is a spectral function that has now 3 sets of matrix elements. There are 2 nested combinations of these energy sliced operators. And one would like to resolve those now as you go to lower and lower scales. But you can see if you do it in a straightforward way, then I'm indicating this here. It's now sort of a 3-dimensional cube that I'm zooming into low energies. Then you can resolve in this fashion situations where all the energy differences are small. So it's a E1 differences between capital E2 minus E1. So in this plane, this energy difference is small. And E2 is any difference between E2 and E3. So in this bottom plane, it's small. So if they're all small, you can resolve it properly. But the question is, what do you do if one of these energy differences, E1 is little, epsilon 1 is large, but epsilon 2 is small. So if epsilon 1 is large, that means you're along this blue plane, but you still want to resolve the difference between epsilon 2 and E2 and E3 very finely. And that was, for many years, the big challenge, how to do that. But then Seung-Sub figured out a way to nevertheless zoom in along this blue slice in such a way that this energy difference is large, but the other ones are small. And he does this in a recursive scheme where he reuses routines written for L point functions, for L prime functions for L. So in this plane here, it's basically a 2-point function that you have to compute. It's a sort of a plane along a weird section through the 3-dimensional space, but within that section, it's a 2-point function. And by doing that systematically, he was able to compute such objects as a function of 3 frequency arguments and 4 frequency arguments. All right, and that's all I'm going to say about methodology. And I also just have one slide about results. Fabian will show you more. So here, he will show you benchmark results also where you can compare with for example, Hubbard-Hund. But here we just applied it to DMFT study of the Hubbard model and looked at the coexistence region where you can have both an insulating solution in green and a metallic solution. And the only thing you should appreciate from my brief point here is the vertex. These are slices through the vertex where you fix, let's say, one of the 3 frequencies to given value and plot it as a function of the other 2. Looks very different in the metallic region from the insulating region. So I think there's a lot of interesting information in there that one can dig out with subsequent studies which are being pursued at the moment. All right, and that brings me to my conclusions and outlook. How much time do I have? 3 minutes, perfect. So the main point methodologically is that by generalizing the way that you compute 2-point functions to 3 and 4-point functions, one can systematically now compute such objects as a function of real frequencies down to arbitrarily small energy differences and arbitrarily small temperatures. And that I think is really exciting. You can do it for both the Matsubara formalism and the Keldysh formalism. And in terms of outlook, since I still have a few minutes, I want to maybe discuss in the context of this conference how this type of work might work. So I listed now some of the other talks and posters that you'll hear here. So one of the goals of this is to apply such methodology also to cluster DMFT systems. And for example, Sasha Lichtenstein will have an interesting talk about plaquette physics in the Hubbard model. So 4-side plaquette, it would be nice to apply this type of thing to a 4-side plaquette. So I think it should be doable. Or multiband models like Hund metals. If you want to compute transport properties, for example, you need vertex corrections, and one could do this now. But for these more challenging applications, one has to improve the accuracy and the efficiency of NRG. And in my group and together with Fabian, progress is being made in this direction. Fabian figured out how to compute self-energies more accurately than was done previously. And there are close relations between NRG and DMRG, which one can, I believe, leverage to really increase the efficiency of energy also. So it's still, although it's a 50-year-old method, still developing with potential for improvements. And then another long-term goal is non-local extensions of DMRG, where you can use either dual fermion formalism or DMFT plus FRG. And Georg Rohringer will give a talk about this. DMF2RG was pioneered by Sabine Andergast and Walter Metzler. And now for that, you have to face the question, how can you parameterize the vertex more efficiently? Because these vertices are really fat objects. They take many gigabytes of memory. And I think people working in this field are realizing it's not, well, it's really expensive. And so there, right now, I think is a period of time where a lot of thought goes into finding efficient vertex parameterizations. So one can decompose it according to asymptotic classes. That was pioneered by the Vienna group. And students from my group, Johannes Halbinger, and here from Thomas Schäfer's group, Michael Meixner, are exploring that. And NRG is actually a nice starting point for checking all these efficient ways of keeping track of a vertex, because we have explicit results for the vertex. Then there's a new, well, last 2 years, Friedrich Green and colleagues advanced idea that one could decompose the vertex according to so-called single boson exchange contributions, which he will give a talk about that, which seems to be very promising. Sarah Heinzelmann has a poster about using that composition together with FRG. And if one would apply something like this to an impurity model, one could check, for example, to what extent this works. We are also investigating to what extent this decomposition is fruitful for the Anderson model. And then efficient data compression. Markus Wallerberger has a poster about sparse modeling of these vertices. The reason I'm mentioning at the end of my talk is I believe all these efforts, which I find very interesting, can potentially benefit from having a benchmark method like NRG to compare against. And since I mentioned FRG, let me also briefly advertise two posters from our group on something unrelated. It's FRG, but on quantum magnets. It's also nice work. Hope you'll go and visit there. All right, with that, let me end. Thank you very much for your attention.